Recording's rolling. It is Wednesday, March 11th. We're gonna pick up today where we left off yesterday on these animated slides. You guys did download the PowerPoint, right? No, so you have to tell me you can't just open it. It's possible. You do have to download it onto your. Okay.
Good. Small nation.
Okay, and we're back. We're back. So tomorrow, you guys know I'm not gonna be here. Have a jury session, so you'll have to substitute. Guys, I'm gonna give you guys a quiz that you guys can do with your teammates. Alright, so quiz with your teammates. It's gonna be on Kinetic Motion we covered yesterday, and forces we're gonna cover today. So you guys are definitely taking notes in your notebook. Guys, this is also gonna be take home quiz. There's 21 questions, so you probably won't finish in class. But you guys can work with each other, and then whatever you don't finish, you can finish over the weekend, turn in on Monday. I'll see you guys then. All right. So guys, a little continuation from yesterday. Let's do a little more tonight before we go to forces here. All right. So here's a good question: Is suppose you know how fast you can throw a ball straight up? How high does the ball go? Okay. Or you could turn that question around. If you know how high it goes, can you solve for how fast it goes? That's these two questions down here. Right. So since we're focused on kinematic, let's definitely focus on this kinematic side. There's of course a different way to solve it with energy, but let's do kinematic. Okay, so say how fast you throw the ball, how high does it go? Which kinematic formula did you guys choose? Here, let me give you guys some options. First, second, or third. You're saying third? Third? Okay. I like the third. Here's why. If you look at how many variables you know or want to solve, right? Guys, maximum height. Whenever you hear maximum height, what do you know about final velocity? 0. Okay, so that could be a known value right there. 0 for maximum height. And you can know the gravity field. That can take the place of acceleration. That's 2 known values. All right, and then here's how fast you threw it, and here's how high it goes. So if you know either one of those, you can solve for the other. You guys that? Okay. And so go ahead in your notes, solve that. Set up this third one. See, the problem with the other ones is that there's also time involved, so you have to have a stopwatch, and there's too many variables. If you pick one of the other ones, there's too many unknowns. Okay? And so we only got so much class time, of course, so here, fast as you can here. So you guys ideally pick that third one right there. That's the most straightforward way to solve this. Okay? And if you're solving for H max, that's like solving for this x here. Actually, this x is this H max. You like that? Yeah, we're going to 0 final velocity. That would indicate maximum height. That corresponds to maximum height. Put a 0 here, x turns into H max. Okay? This A I replaced with negative G because you're throwing it upwards, gravity's pulling downwards. That is a difference of direction, isn't it? There has to be a negative somewhere in there. Okay, and what did you guys come up with for H max based on how fast you threw it? There you go. Just a little algebra. Okay, you do set up, little algebra, switch around, get that. Okay. Here's another question. Probably a more practical question is if you know how high you threw it, maybe get some friends and you throw it and it goes up to like the 6th story or whatever. Okay. It's probably easier to see how high it goes. Can you determine how fast you would have thrown it? All you do is take this expression, you just rearrange it and solve for V. And what do you get? 32GH. Yeah, no surprise, right? And then if you do energy, right, which is not going to be on the quiz tomorrow, but that's how you would set it up, and it leads to the exact same set of answers. Okay. You know what will be on the quiz tomorrow? I do want to hit though is turntables. There's a little bit of rotational kinematic. There's just one question, I think. One question. So let's review this real fast. How far you've moved? Like guys, what if there's a big circular racetrack? You look in the odometer on your car. It says how far you've driven. Right, that could be this x. Okay, so what formula? How do you finish this off right here? What? Yeah, there you go. Theta r. Right. So how far have you gone around in an angular sense times your distance from the center? Okay. Now, guys, there's a catch though. This theta, can this be in degrees? No, has to be in radians. That's the only way for this formula to work. Has to be in radians. Okay? If you're working in degrees, it has to be inside a sine or cosine and the or tangent, and the calculator has to do that. Right. Could you guys fill in these other ones too? Right. So theta is your angular displacement. How far have you gone around, like in radians? This omega right here, omega, that's how fast is the turntable turning, if it's a turntable. Right. I'll get you guys labs too. You guys remember that turntable friction lab? It's going to be after this quiz. Right. Right, and then angular acceleration, this alpha right here, could be what if the turntable is speeding up or slowing down and spinning? Okay. And you guys remember these 3 rotational kinematic formulas. They're analogous to the same three linear formulas. So instead of the linear distance in meters, we have angular distance in radians and so on. Right, here's angular speed. Right, time is still time. Okay. Okay, you guys know all those? They'll navigate this. Okay. Yeah. There's one question on your quiz tomorrow / this weekend. Okay. Right. How about turntable slows to a stop? We'll go through this kind of fast. Let's start with this one right here. Guys, what does omega versus t look like for slowing to a stop? Slowing to a stop. Boom. Right. It was spinning. Now it's not. What does angular acceleration look like? Yeah. So in this class, we're looking at uniform motion. Boom. Right. Finally, did you guys do car braking to a stop yesterday? Are these graphs looking about the same? All right. So what shape do you think theta versus t is going to be? No, it's not a square root. It's not a square. It's an upside down parabola. Upside down parabola with the vertex right here. Upside down parabola. Right? Okay. So it's still rotating in the forward direction, but it's slowing to a stop. Notice it never rotates backwards. All right. Okay, and then these are all related to each other. Boom, boom, boom. Okay. All right. Forces. Okay, I think you guys know these. These kind of fast. Masses in kilograms. Forces in newtons. There's two ways to represent weight. Force, friction force, coefficient of friction, tension, spring constant. All right, you guys know all those, right? You know all this? Boom, boom. All right. What's the Newton's first law? There you go. Law of inertia. You guys know law of inertia? Yeah, we only got so much class time, so we go through these kind of fast, but should be reviewed. You guys should know these. I like that. Oh yeah, you just say that. That would get you full credit. Right, you can spell it out in a sentence for him. Right. There's a little okay. Third law.
Every action is an equal and opposite reaction.
Yeah, equal and opposite forces rule. Equal and opposite forces. Right. Now, guys, whenever I have you draw a free body diagram, normally you're focused on like either a single object or sometimes a single system. So the equal and opposite force a lot of times won't even show up. Like if I just say a free body diagram only on this cannonball right here, just cannonball. It's like, oh, there's only one force. It's the blast force. Where's the equal and opposite? The equal opposite, you have to consider the cannon. Okay. All right, boom, boom. All right, so let's say you got a ball on a string. It's going around a circle. Zoom, 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 zoom. And then the string breaks right here. Which way does the ball fly? Does it fly straight away from you? Or does it follow this green arrow? Law of inertia. Yeah, tangential velocity. Acceleration, bridge variable. Do you guys remember the other day we were doing the guy was pushing the box to the elevator? This is one of the ones that came up. Because the box had to get to the elevator in so much time, therefore you could solve for the acceleration going through one of these kinematic right here. Okay. And then you say, oh, the question was how hard does he have to push the box? Now there was a net force on the box because he was pushing the box, but also there was friction acting on the box. So the difference in forces result in the next net force. You guys remember solving that? Right. So we did that the other day, the most recent FRQ we did. Okay. What does 1 Newton break down into? What? Yeah, kilogram meter per second squared. Does that look a lot like Newton's second law of motion anyway? F equals ma, right? What is pressure in pascals? Be Newton per square meter, right? Force per unit area. Okay. I don't think AP has too many questions about pressure though, but it's good to know. Right. Force per area. All right, boom, boom. Got that. Pythagoras cut. Hey, you guys remember Pythagoras cut? Okay, got that. All right. Hooke's law. What's the formula? Hooke's law.
F equals kx.
Yeah, F equals kx is a good one. Now this could be the applied force to either stretch or compress a spring. Right? And by the time we got to energy, which wasn't for a few more weeks, we said, well, the area under the curve could be spring potential energy, but that's not going to show up tomorrow. Okay? Now a lot of textbooks actually talk about Hooke's law in terms of the restoring force. So if you compress the spring, isn't the spring actually pushing back the other way? Or if you stretch the spring pulls back the other way, right? So they just throw in a little negative there. Yeah, okay. So if you see that, right? Sorry, same idea. Boom, boom. Okay, in lab. All right, free body diagram. We're going to show all the forces and moments. Let's say torques acting on an object. Now, in this class, typically we're just looking at the forces. Yeah, you could also draw like if there's some kind of rotational moment, like a torque acting on it. Right. But by the time we got to that part of the class, you guys remember rotational dynamics, right? Is what we ended up doing instead was creating force diagrams instead, and we just showed the location of all the forces. So really in this class, we're just going to list the forces. Okay? Guys, are velocity vectors forces? No. So velocity vectors are not part of free body diagrams. right, here we go. We're gonna draw a bunch of free body diagrams. Go ahead, do your notes. Draw a rocket at constant velocity in deep space. Deep space, constant velocity. Constant velocity, maybe 10,000 meters per second, just screaming through space. All right, what force did you guys draw on that rocket? Nothing. That's right, because there are no forces. Right, so key here is concept velocity, guys. Concept velocity. Concept velocity, you know the net force is 0, and if you're in deep space and there's no gravity forces and there's no air drag or nothing like that, yeah, there's just no forces at all. Right? It's just going. It's just going. You don't need any forces. Draw nothing. Right. All right, air hockey puck. Yeah, draw. So it's going. Let's say across the horizontal air hockey table. It's just going. Right, drawing free body diagrams. Right, everybody's writing this in the notes, right? Right, help you guys out for quiz tomorrow. Right. Right, what do you guys draw?
Force,
Yeah, okay, there's the weight down, there's the air jets going up. Now, if this hockey puck is already in motion, it's already going, are there any horizontal forces? No, of course we're ignoring the air drag. Now, when you got it going, when you hit it with the paddle initially, right, that was a force, right? But that's already happened by the time it's in motion. Okay? That was in the past. Right. Say you're pulling a block across a table, constant velocity. So horizontal surface, constant velocity. What does that look like? Go ahead, draw all those. Draw those. All the forces. Just dragging it horizontally across the horizontal table surface at constant velocity. Okay. Because anytime you see constant velocity, what do you know about the sum of the forces? 0. Yeah, they should all zero out. Okay. You might have some vertical going on and some horizontal going on. And in fact, they should zero out along each axis, shouldn't they? Along the y-axis, along the x-axis. Okay. All right. So what's one force you guys drew? Yeah, the weight. Okay. So F sub g or mg. Well, what counteracts that one?
Normal force.
Yeah, the normal force. Right. So those are going to balance out. Right. Yeah. Okay. Here, pull it to the right with the springs. Yeah. I might call it force applied, or you could do force spring. That'd be okay too. AP would get credit. Right. Or you could do F sub pull. Yeah. So they'll accept any of this. Yeah. And then friction force. Right. And notice that, yep, the two verticals cancel out and the two horizontals also cancel out. And that would result in a type of equilibrium because it's constant velocity. Right? There's no acceleration. There's no net force. Right? All right, here's coefficients of friction. Right, different. So coefficient of friction is a material property, right? Guys, where is it easier to break it to a stop? Let's look at these last 3 rows right here. Got an icy road, a wet road, and a dry road. Okay. Which one's easiest to come to a stop?
The dry road.
Definitely a dry road. You guys see the largest coefficients of friction on a dry road? Right. And these are kind of round numbers too, right? Depends exactly on the asphalt and da-da. All right. Here we go. A little more challenging. Guys, what is the acceleration of the car in terms of the coefficient of friction, the mass of the car, the gravity field, whatever you think the relevant variables would be? Go ahead. I'll just give you that slide, and you guys create the rest. Create a free body diagram. Do a little bit of do a little proof on the side there, and tell me what is the acceleration of the car in terms of relevant variables. What do you think? Questions are getting harder. Or you might say deceleration since it's braking, or negative acceleration. Well, maybe that's a hint. Maybe the answer should be negative. Okay. At what rate is the car allowed to slow down? Ooh. You guys got free body diagram. You guys are doing some equations. If this was an FRQ, this might be worth a few points. Maybe they would want you to start with something off that equation page. Okay. And maybe substitute something. Do a little algebra. Right, show of hands. Who has the answer? Who thinks they know the answer?
I don't think I know. I have A.
Wait, let me see.
I got that answer.
Here to see if somebody got it right.
You
Got something? Ooh.
Wait.
Wait, yeah, that's it. Yeah, Justin got it. Justin got it.
Right.
Did anybody else get this? Get the whole thing? Okay. I think some of you guys are close or on the right path. Okay. Yeah, this is the first part. You may have picked up point here, 2 points there. Okay. And yeah, Justin would have got all the points because Justin got the whole thing. And so, guys, what's here, free by diagram? What forces did you put on this car?
Gravity.
Yeah, the weight, the normal force, and the friction force to slow it down, and that's it, isn't it? That's the 3 forces, right, on the car. Okay. What's probably the first line you should write up here?
F equals M.
Yeah, F equals ma. I like that. Now this F is really the net force. Oh, I see 3 forces. What takes the place of the net force? The friction. Now I did one more thing. I threw in a negative since it looks like positive direction can be to the right and friction's to the left. So I went ahead and just call it negative. Right. Now if you were given the coefficient of friction and the mass of the car and so on, we could do some more substitutions. What can you substitute in place of friction force?
Normal force times the coefficient of friction.
There you go. Coefficient of friction times normal force. Yeah. And results in car slowing down. Okay. Oh, but what is this normal force equivalent to?
Mg.
Mg. And that's useful because the mass of the car cancels out. You guys remember that? Or you're driving to Publix to get your Thanksgiving Day groceries with an empty car, and then you're driving back the other way with a car full of groceries. And it's the same braking distance. If you're braking to a stop, the car will slow down at the same rate, regardless of the mass. Yeah. So that's a pretty good one right there. All right, guys, if you did not get that, then be practicing that. You guys know the AP exam's in a few weeks. You guys know you can download this whole file, has all the animations. May 6th. Yeah, May 6th. Ooh, May 6th. It's coming up.
What?
Plane constant velocity. Constant velocity. If you go into the military, they're going to ask you this question. They always say, "What are the 4 forces on plane constant velocity?"
My dad keeps telling me about these forces.
Yeah. All right. So, what do you guys come up with?
It's like, how do they draw it out with your anything? There's 4 points. I have 4 points. I'm back. I don't know. No, yeah, no. I don't know if this is final one.
Did you say that?
All right, here we go. You guys say the plane has a weight? Has a weight? Well, what's? Oh, okay. How about a thrust force? Okay. Maybe the engines are pushing against the air, and that's what's providing the forward thrust force. Do you guys think? Okay. Yeah, lift. Right. Now, there's a couple things that contribute to lift. I should know which counts more. But guys, the wings are tilted a little bit so that because there's a thrust force and the plane is going forward, that also makes it go up. Right? But also, do you guys remember learning about Bernoulli principle? Bernoulli principle? Right. Actually, I want to draw something for you guys. So one more thing. There's also a drag force, right? Right. And that would put it at constant velocity. Let me draw something for you guys. Okay. So there's a couple things that make the plane fly. And how much it weighs factors. Okay. But one thing is that the wing is tilted up a bit so that as the plane flies forward, it'll like push it, like force it up. Okay. But yeah, the Bernoulli part of this is if you actually look at the shape of the wing, it's actually shaped more like this, isn't it? Like curved on top and more like flat on the bottom. Right. So that as these air currents are coming through, right, and you get all this air flowing. Do you see, guys, which air molecules have to travel a further distance across the wing, the top or the bottom? The top that actually travels further distance. And if it takes the same time, guys, if you go a further distance at the same time, what's your speed?
Increasing.
Yeah, we'd be faster speed. So do you guys think this is I'll call it B fast, I'll call this B slow? Right? Like a fast speed and a slow speed? Right? And what do you guys know, going to Bernoulli now, happens to the pressure and fluids that move fast? the pressure drops. Ah, do you guys see a pressure differential? Yeah, that's also part of help with 25. Pressure differential. Alright, boom. Ooh, projectile. Okay, so you throw a ball. Now, right after the ball leaves your hand, here comes a projectile. It's gonna fly through the air. Maybe I take a picture every second for like 7 seconds. Okay. Alright. What's the free body diagram at each of those points? Let's get rid of air drag. There's no air drag. No air drag. Maybe I should have written that too.
I don't want to call that 17. I did. Where are you going? Maybe we did it to complain about it.
Okay, so, guys, what's the free body diagram right after it leaves your hand? Yeah, MG. What about 1 second later?
MG.
MG?
MG.
That's it. Guys, it's a free fall. Anything in free fall. And we're ignoring air drag.
There is no. It's a normal force. There is.
Yeah, guys, is that ball in equilibrium? No. There's a net force, which is its weight. It's accelerating. It's accelerating, right? At 9.8 meters per second squared down.
And there is no.
Alright. If you see the word free fall in this class, that implies no air drag. Would that just be its weight? That's what we just did. That was last night. Now let's say you drop this ball off a cliff and it's falling straight down. Now let's put some air drag. Some air drag. Right, which they'd have to spell that. What does that look like with some air drag? Yeah, some resistance. Right. Guys, is that middle object right there still accelerating?
Yeah.
Yes, because there's a net force. Right. So it's still going faster and faster. Right? Do you guys think this drag force is dependent on the speed against the air? Yeah, it turns out it's proportional to speed squared. So as it's falling faster, which it is falling faster, it's speeding up. Okay. Is that drag force still increasing? And that process will continue until what happens?
Velocity.
Yeah, terminal velocity. Right. And then when those two balance out, is it still falling down?
Yeah.
Yes. Is it still speeding up?
No.
No. Okay, so constant velocity. Right, so equilibrium. Right. AP doesn't really get so much in a drag force, but you might see this in college. Guys, if you go engineering in college, probably see here drag force proportional to v squared. Right, got coefficients of drag. Okay. Actually, let's go and do this one. Let's do this one. Here's good critical thinking. Okay. So we are considering air drag. We're at the edge of a cliff. We're gonna drop this ball. Okay. Okay, guys, if you drop the ball, how fast is it moving at time 0?
What?
0. So can you guys go ahead and put a point right there? Point at 0, 0. 0, 0. Okay. What do you think the rest of that graph would look like with air drag?
It will get to throw a ball.
What does it look like without air drag?
That's what I'm thinking.
Yeah, it's just a linear relationship, like y equals kx. Or I should say d equals at, right? Or d equals gt. Okay. But now if there's air drag, it's a little bit different. Good critical thinking here. What if you guys figure that out? What's that gonna look like with the air drag?
I was doing.
It's the other one.
Gonna get the.
Yeah.
So you got it. Yeah, so got it. Yeah, right. Look, you got it. Joe got it. Yeah, Lily got it.
Justin didn't go.
Alex got it. Yeah, Chloe got it. Okay. Yeah, you guys get this. Okay. So what you guys said is that it's gonna eventually reach a terminal velocity, which is a constant velocity value. Okay? But it'll start by accelerating. In fact, the initial slope will be the gravity field because there's like almost no air drag or no air drag at all, right? But then as it falls faster, it eventually tends toward this constant velocity, which is the terminal velocity. Yeah, right. You guys see that? Put it all together. All right. Oh, weight hangs in equilibrium. What's the two forces on this guy? Yeah, mg down and the spring force up. Boom, boom. Right. So you could say sum of forces y direction of 0. Right. So equilibrium. Guys, anytime you see the word equilibrium, you know the sum of the forces is 0. Right? That's probably a good way to go about it. Okay, so one force down, one force up, 0 out. So you can say something like that. Okay. If I told you any 3 of those variables, you could solve for the 4th one.
Yep.
You do that. Okay. Ooh, how about this one? Guys, draw the diagram there. Diagram there. What are the forces? Stand that central node where everything's come together, right? The weight, each spring scale, there's one point where they all come together. So let's do the forces at that central point. I put a big black dot right there.
Another one.
What does this look like? Now, AP usually uses, yeah, okay, yeah, I see you guys get this right. Oh, that's right, that's right, that's right. AP usually uses the phrase, draw the forces, not the components. We'll go an extra layer. Also, look at the components too. All right, so what you guys came up with was you said the weight's pulling down, each spring force is pulling along the direction of the spring, right? That's typically true for like springs and strings, is that the force is directed along the same direction. Okay. Here, guys, little side thought. Do you guys remember that ladder leaning against the wall from rotational mechanics? Do you remember that? Okay. In that case, there was an extra detail. If you have a stiff, like rigid object, like a ladder, that's not necessarily the case. The forces don't necessarily line along the ladder, but a string that, or in case of spring, that would be. Okay. Now, guys, let's go an extra layer. Could you introduce a Cartesian system and break some of these into components like that? Maybe break those diagonals into components. Okay. And if you do that, how much is this pulling left versus how much is this pulling right?
The same.
Yeah, the same. They have to balance out. And then how much does this pull up and this pull up versus this down? Also balance it. Yeah. You can say that too. If this is a 10 Newton weight, isn't this 5 newtons up here and this is 5 newtons up here? Yeah. Okay, so some of the force X and the Y each go to 0. Okay. Okay. What if it's asymmetrical? Because last slide was symmetrical, like about the vertical axis, but now this one's all wonky looking. Okay, so let's have the weight down. I mean, it's getting kind of similar, but a little different. There's maybe the left force and the right force. Okay. Guys, which force do you think would be larger magnitude, the left side or the right side? Guys, think about that for a little time. They're not the same.
They're not the same.
Yeah. Which force has to be the bigger force?
Is it the right side?
You saying the right side? Okay. Show hands. How many guys agree with Daniel? Say the right side. Yeah. Okay. And the analysis I would do to get there is I would look at the components. Right. So, hey guys, is that blue left component and that blue right component? Those cancel out. Those cancel out. But what about the verticals? Guys, which one has a greater vertical component? Right. Has to be the one on the right because of how the spring is angled. Again, the force has to be along the direction of the spring scale itself. Okay, so the overall force on the right does have to be bigger. Yeah, the spring scale rating on the right is more than the spring scale rating on the left. Okay. All right, here's the equations that go with that. Boing. Yeah.
Don't the scale forces have to add to the gravity?
Yeah, the green components do. Yeah, the green components. Right.
Oh.
So like if this weighs 10 newtons, suppose you have a 10 Newton weight. Right. This component right here might be 3 newtons. And this one on the right might be 7 newtons. And the 3 up here and the 7 up here cancel out with the 10 down here.
So how would you know how long you should make the arrows?
I would have in my mind, I would be thinking about these components, right? And AP usually does not want you to draw components. If you really have to draw them, then dash them. And usually they say, okay, well, if you dash them, then that's okay. Right? At least that's what AP graders have told me in the past. Okay. But yeah, I would think that and say, okay, I want the left and the right to be able to cancel, and I want the 2 upward components to be able to balance out with the downward component. Right? And here's with the sine and the cosine. Right? You guys can come up with equations. Ooh, you guys see a nice system of equations there? System of equations. Okay. Now, guys, let's keep track of variables. Because, guys, if you can come up with a system of 2 equations, which is what I have this equation here and this equation here, right? You're allowed to have how many unknown variables that you can therefore solve for? Also 2, right? Right. So, for example, if you knew what the weight was, it's like, okay, I got a 10 Newton weight. And let's say you took a protractor and you measure, okay, here's alpha and here's beta, and I measured out the angles, yada yada. Okay. You could calculate the force right and the force left. There's enough information there to do that, right? Or if you instead read the spring scales and say, okay, I know what the force left is and I know what the force right is. Could you, in principle, calculate alpha and beta? Yeah, you could.
How did it?
Yeah, you guys remember doing this lab? You guys remember doing those 10 mini labs? Those 10 mini labs? This was one of the 10 mini labs. So you were changing this angle, and what was happening to the spring force? So let's have a 10 Newton weight. Can you guys imagine a 10 Newton weight? What if this theta from the vertical is 0? So you're pulling like up and up. What's the force in each spring scale? Okay, guys, I'll say it again. I got a 10 Newton weight, 10 Newton straight down. And what if this theta goes to 0? So both spring scales are pulling straight up. What's the force in each spring scale? Like 5 and 5, right? 5 and 5? Okay. Right. Then as you change this angle, make it 10 degrees, 20, 30, 40, 50, and you make it closer to 90 degrees. What's happening to the force in the spring scales? As they pull it closer to a T shape, do you have to pull harder, harder, harder? So the spring force must be going larger, larger, larger. Right. Guys, can you ever make a perfect T? Can this theta ever go to exactly 90 degrees? No, it cannot, because there has to be some vertical component. Like if this is a 10 Newton weight, there must always be 5 up here and 5 up here if it's symmetrical, right? Okay, so you can never make a perfect T, right? Which tells you something about this graph here. Here's tension as a function of angle, right? So kind of a continuation of the story we've been walking through. Okay. Do you guys remember what this looks like? Does this have a vertical asymptote? At what angle? At 90 degrees? Remember, because this theta can never reach 90. That would be a perfect T. You can't do that. Right? You can't create a perfect T. Right. So at 0 degrees, what was the force again? Like if this was 10 newtons and these spring scales are pulling up, like exactly up, wouldn't it be 5 and 5? It should be like mg over 2. Right. What does the rest of that graph look like? What do you guys think? Right, I want you guys to imagine that before I just show you the answer. Right, so good critical thinking again. I guess if you know how to read that equation up there, I'll tell you what the graph looks like. Okay. What do you guys think that would look like? Right. You guys remember vertical asymptote? That's not a curve you really see very often in this class, but. Alright. Very on frame. Did I have you guys build one of these? Okay, yeah. Alright. Did I show you guys the slinky drop?
No.
What? I didn't show you guys the slinky drop? Hold on, we're gonna do a pause right here. I'm gonna dig this up. This file. Slinky drop. Where's
Yeah, slinkies? The underrated one. Are you in? Are you attending force
But this is going to be really tough to see. So how are we going to actually, till the whole slinky head collapse, you let go of the top. You wait, you let go of the top. You wait, you let go of the top. You let go of the top. You let go of the top. It waited until the whole slinky head collapsed down to the bottom before it itself moved downward.
Ooh, pretty cool. Hey, train gang. Train gang. Let's do the train gang. So, guys, what if this train is accelerating? Now, that's part of this. The train is accelerating at some value. Right? Maybe there's a force from the engine. Maybe the engine is providing a force. I'm thinking about the question as I phrased it that you guys are about to get tomorrow on your quiz. Right? There's some force here. Does the force have to pull all 3 masses? Could you do Newton's second law, F equals ma, and do the sum of masses, the force, and then divide and get the acceleration? Okay. So now you have the acceleration from Newton's second law. Right. All right. Now you have some value for acceleration. What is the tension in this link right here? T1. Ma. Right. What's the tension in this link right here? It has to pull both of these masses and make it accelerate. How about this one right here? Be like that, wouldn't it? Okay. Which guys, which tension is the greatest? T3. Right. And here's another question on the side. What if there was no acceleration? I've been saying the train's accelerating, but what if it wasn't? What if it was just constant velocity? What would each tension be?
0.
Yeah, 0. There'd be no tension at all. Just from inertia, they'd all just be rolling. Right? Ooh.
Oh no.
Normal force derivation. Yeah, let's do. We got that. Let me see what this looks like here. Where's my PowerPoint? Okay. Whoops. Sorry, I didn't mean to give you guys that, but hopefully you would have figured that out, right? Right. You guys figure out this is a Newton's second law question. So, guys, the very last line says normal force equals something. So go ahead and do the full derivation. This one you guys need to know. AP is going to ask you this, or some version of this. I don't know if it's going to be a multiple choice. I don't know if it's going to be an FRQ. But it will be helpful to be able to derive the types deriving right now. So figure out what's the normal force rating on the scale. It's also called apparent weight. Because if you're standing on that scale, right, let's say normally you weigh 100 pounds, and you stand on that scale and the elevator accelerates upward, maybe it says you weigh 110 pounds. Like, whoa, I feel really heavy. So that upward, your apparent weight would be the normal force reading on the scale. Okay. All right. What's the next line you guys wrote right here? Yeah. So normal force minus the weight, that is the net force. Okay, so that's what MA is. Okay. Maybe that could have been a single line, whatever. Okay. And what are you solving for again? Normal force? Oh, can you do the algebra?
Yeah.
Just slide the MG over? All right. Yeah, you could factor out an M if you want. Could look like that. Like that. Yeah, I've seen that a bunch of times. Okay. Now this is for an elevator that's accelerating upward. Guys, there's two ways to accelerate upward. One way is you could go up faster, couldn't you? Up faster, faster. But there's another way. What's the other way you can also accelerate upward? Yeah, moving down, slowing to a stop. Yeah, moving down, slowing to a stop. Which would also be that. Yeah, okay. All right, you guys got that in your notes? Got that? Oh, there we go. Boink, boink. All right. How about all these scenarios? All right, so, all right, here's accelerating down. Here's equilibrium, which could be at rest or constant velocity. Guys, if you're going upward at constant velocity in the elevator, inside the elevator, does it feel identical to standing on the sidewalk? Yeah, you can't tell the difference. It's all equilibrium. Okay, and then here's accelerating upward, which we just did. Okay. The change I made is I made this a tension force for the tension in the elevator cable, but it's the same math, isn't it? Okay, that's good. All right, classic Atwood. All right, let's put different weights. What's some other forces I could also throw on the board here? Tensions. Yeah. All right, so go ahead. Write as much as you can there. I've got 4 boxes outlined, and what goes in those 4 boxes? So, just to remind you guys, there's difference of approaches to these. If you take business in college, they might do a system of equation approach. They might start with the 2 green boxes at the bottom. But I walk you guys normally through a whole system approach. So I'm looking at the whole system. Okay. Actually, here, I'll reveal this top box. Guys, the top box is really general. What goes in the top box? Newton's second law. Okay. All right. So I look at the how I prefer to do it myself is I'll look at the whole system, and I'll write Newton's second law of motion. That can pick you up a point itself. Okay, and then I can get everything else from there. And so, what's the overall acceleration? The other day when you guys were taking the SAT, some of you guys were taking the SAT, and some of you guys were in here. If you watched the video from that day, we solved one of these. All right, what did you guys write in this yellow box? Yeah, it's difference in weights because one's pulling clockwise, one's pulling counterclockwise. Right? But it's the sum of masses because that's the total inertia being moved around. So that's Newton's second law, whole system approach as it applies to double elevator Atwood. Right now, guys, what if you wanted to find the tension in the string? Could you do that?
Yeah.
Oh, I think that's what these other 2 green boxes are for. And notice the green boxes are honed in for specific masses, either only mass 1 or only mass 2. Okay, so now we're focused on an individual mass instead of the whole system. Guys, what'd you write in these boxes? Boom, boom. Okay. Hey, you guys can come up with all that. Okay. And of course, if you watch the video from the other day, like the SAT day, then I threw some numbers on the board. So we call them so many kilograms, so many kilograms. Said, how's that thing gonna accelerate? Okay, while you guys are finishing writing that down, could you come up with another follow-up question? Like, okay, how about a kinematic question? I could think of several kinematic questions. How far does it move in so much time? How fast does it move in so much time? And how fast is it moving after some distance moved? Right? There's 3 follow-ups that you could ask right after you get acceleration.
Once you get acceleration, you can do whatever.
Right, you guys good on the Atwood? Hey, it's another Atwood. Right, boom, 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 boom. Usually there's zero friction force. That's why I made it really light gray, so it doesn't really draw too much attention. Right? I think this tension is just internal to the system, just like before. I think you're gonna start with Newton's second law, right? Or if you do the same approach we did last time, right? Hey, go ahead. What do you think the rest of those boxes say? Okay, so it's what is the net force on this entire system? Yeah, just M1G. That's it. Because this hanging weight right here is providing all the force for this thing to move. And how much mass is being moved around? Well, both these masses, so you add them together. Oh yeah, that's assuming no friction is what I said. Now, if there is a friction force, you'd have to, of course, subtract that off in the numerator. Right. And then do you think these two green boxes have to do with looking at the tension also? Right, so you could solve for the tension either that way or that way. Okay. Boom, boom, boom. All right. All right, you guys did classic Atwood, you guys did modified Atwood, those were labs. Ooh, block and equilibrium on incline. Equilibrium on incline. Right. His equilibrium might be at rest or might be sliding at constant velocity. Are you guys going to introduce a Cartesian system that runs parallel perpendicular to the surface? So I'm already thinking of that rotated Cartesian system. Guys, what's one force on this block?
MG.
Yeah, it's weight. What's another force? Normal force. Oh, whoops, I forgot. Let's split that in components. Think about. Right. Notice I dashed the components. I didn't make those solid. I dashed them. Right, there's the normal force. And is that in equilibrium yet? That's not in equilibrium yet. Need a friction force. There we go. Okay, now it's in equilibrium. Aha. Equilibrium. Okay. And is the normal force equivalent to mg cosine theta?
Yeah.
And what's the friction force equal to? Mg sine theta. Again, as long as it's equilibrium.
This is going to the fun. I like the box line now.
Boom, boom.
That makes sense.
Zero friction incline. Guys, if you get a zero friction incline, you guys remember those Hot Wheels cars going down the incline? We're going to get rid of the friction. Friction's gone. You can solve for the acceleration. Does anybody remember what the acceleration comes out to? See if you can solve it. Because what's the net force on this block? There is a net force now. mg sine theta. mg sine theta. Now what? Boom. Boom. Oh yeah. You guys see do that? So when you guys were sending those Hot Wheels cars down the incline, that's how much your cars were accelerating. No, that was way early in the year, so you didn't know that at that point, but now you did. Okay. What about constant velocity, which is completely different, because now the friction's back. We got friction back. Friction back. Now, a really good question would be, what's the coefficient of friction to make that happen? You guys did this lab. Do you guys remember doing this lab? Right. Now, this is a little more involved. Right, so here, I'm going to walk you guys through because we only got so much time. So we got that. Is that okay so far? Is that okay? Now I'm going to say this friction force and this mg sine theta are balancing out. Is that okay? Okay. All right, and let's go through step. So that has to be true. Guys, what do I replace friction force with? Yeah, like that. Is that okay? What do I replace normal force with? G cosine? Oh, what cancels out? The mg? And what is sine divided by cosine? Boom. You guys remember that? Remember that? Right. That was a little more involved. Okay. But you here, you guys took me through step by step. You guys told me every step of the way what the next step was going to be. Atwood incline. Yeah, if you take physics in college, you'll see more questions like this too. So here's the full solution. Right. Now, if I'm doing a whole system approach, you guys see a whole system approach? That's where I'm circling those three forces and I'm saying those are going to be the relevant forces. Okay. So there's Newton's second law of motion. Well, okay. Now this whole thing isn't solved, but it's set up. You could solve this, right? That's how you set it up. Okay. All right. Alright. Oh, the car turns on a flat track. What does it look like from above? Alright, friction force. It's making a left turn. What does it look like from behind? Left turn, left turn. So the friction between the tires and the road lets it make the left turn. All right, one more slide. Here's the last one. What's the free body diagram on this pendulum swing? Is it the same weight over and over? And the tension pulls along the direction of the string. Okay. All right, and that is a perfect timing. Yeah. All right, so hope you guys have a good day tomorrow. I will see you guys Monday.